Good day, everyone. This group will be discussing gases. This will include the common units of pressure, which will be discussed by Ms. Sabales. The gas laws will be discussed by Mr. Yao and Ms. Brusello. And the last is the ideal gas equation, which will be discussed by Ms. Tunina and Ms. Dolan. Pressure is the force per unit area of a gas. It allows metal boats to float, airplanes to fly, straws to suck water, balloons to hold their shape, and even describes the interaction of all materials with any force. Pressure of gas depends on the concentration, volume, and temperature of the gas. The common units of pressure includes the Pascal or PA. It is the standard SI unit of pressure. The atmospheric pressure in pascals is 101,325 PA or about 100 kilopascal. Pascal is used to describe strength, stress, elastic modulus, and hardness. Kilopascal or kPa is often used in favor of pounds per square inch or PSI. Another unit is the standard atmospheres or ATM. It is defined as 101,325 Pascal. It was originally designated as the air pressure at sea level. Standard atmospheres are commonly used when the precise air pressure is unimportant. Next unit is the manometric units, which includes millimeter of mercury, millimeter of water, foot seawater, and meter seawater. They can vary from location to location depending on the density and temperature of the liquid, and this makes them imprecise. Another unit is the inch of mercury or INHG. It is a non-SI unit of measurement for pressure and is used for barometric pressure in weather reports, refrigeration, and aviation in the United States. Next unit is the torr or TORR. It is useful for measuring very small pressures. In terms of atmospheric pressure, 760 torr is equal to 1 atm. Another unit is the pounds per square inch or PSI, which means the weight of a pound times the force of gravity per square inch. Next unit is the bar or BAR. It is a metric unit that is same as 100,000 PA or 100 kPa. It is used especially in meteorology or weather forecasting. Another unit is the technical atmosphere or AT. It is the metric equivalent of PSI and is measured in kilogram force per square centimeter. Next unit of pressure is the barad or BA. It is defined as 1 dyne per square centimeter. The last unit is the piez or PZ. It is the standard unit of pressure in the MTS measurement system, which was used in the Soviet Union or perhaps 18th century France. It is defined as 1 sten per square meter.
The gas laws. The gas laws is composed of 4 primary laws, namely Charles' law, Boyle's law, Gay-Lussac's law, and Avogadro's law. The Charles' law. The relationship between the volume and temperature of a given amount of gas at constant pressure is known as Charles' law in recognition of the late French scientist and balloon flight pioneer Jacques-Alexandre César Charles. Charles' law states that the volume of a given amount of gas is directly proportional to its temperature on the Kelvin scale when the pressure is held constant. It gives the relationship between volume and temperature if the pressure and the amount of gas are held constant. First, if the Kelvin temperature of a gas is increased, the volume of the gas increases. Second, if the Kelvin temperature of a gas decreased, the volume of the gas also decreases. This means that the volume of a gas is directly proportional to its Kelvin temperature. Think of it this way. If you increase the volume of a gas and must keep the pressure constant, the only way to achieve this is for the temperature of the gas to increase as well. According to Charles' law, if the pressure of a gas is held constant, increasing the temperature of the gas increases its volume. What happens when a gas is heated? Its particles gain energy. With more energy, the particles have a greater speed. Therefore, they can move more and spread out farther. The volume of the gas increases as it expands and takes up more space.
Let's have an example of Charles' law. The problem is 10 liters of hydrogen gas at 27 degrees Celsius is held in a piston with constant pressure. If the pressure is raised to 327 degrees Celsius, what would the volume be? So we're going to list the given here. The given are volume 1 is 10 liters. Pressure 1 is 27 degrees Celsius, equivalent to 300 Kelvin. This we're going to find the volume number 2. Temperature number 2 is 327 degrees Celsius, equivalent to 600 Kelvin. So the formula is V1 over T1 plus V2 over T2. Substitution. T2 is 600 Kelvin. Cross multiplication. 10 times 600 equals 6,000 liters Kelvin, and V2 multiplied by 300 Kelvin equals 300 Kelvin plus cancel V2 equals 300 6,000 divided by 300 equals 20 liters. So the volume 2 here is 20 liters. It's right here.
Boyle's law, also called Marriott's law, a relation concerning the compression and expansion of a gas at constant temperature. This empirical relation, formulated by the physicist Robert Boyle in 1662, states that the pressure P of a given quantity of gas varies inversely with its volume V at a constant temperature. The relationship was also discovered by the French physicist Edmé Mariotte in 1676. Boyle's law states that the volume of a given amount of gas held at a constant temperature varies inversely with the applied pressure when the temperature and mass are constant. The reduction in the volume of the gas means that the molecules are striking the walls more often, increasing the pressure. Conversely, if the volume increases, the distance that the molecules must travel to strike the walls increases, and they hit the walls less often, thus decreasing the pressure.
So let's have an example at Boyle's law. The problem is a sample of hydrogen has a volume of 10 liters at a pressure of 1 atmosphere, which is equivalent to 100 kilopascal. If the pressure is raised to 2 atmosphere, what would the volume be? So the given is pressure 1, volume 1, pressure 2, and volume 2. The first pressure is 100 kilopascal. First volume is 10 liters. 200 kilopascal. And we're looking for the second volume. Since the formula is P1 equals P2. Let's substitute. 100 kilopascal times 10 liters multiplied by P2, 200 kilopascal, V2, 100 times 10 equals 1000 liter kilopascal, 200 kilopascal volume 2. So divide both sides by 200 kilopascal, 200 kilopascal. Cancel. Volume 2 equals 1000 divided by 200 equals 5 liters. So the volume 2 is equals to 5 liters. Let's write it here.
Gay-Lussac's law states that the pressure of a given mass of gas varies directly with the absolute temperature of the gas when the volume is kept at a constant. Gay-Lussac is recognized for the pressure law, which established that the pressure of an enclosed gas is directly proportional to its temperature, and which he was the first to formulate, meaning the proportioning or ratio will stay the same. The equation for Gay-Lussac's law can be written as P1 over P2 equals T1 over T2, or pressure 1 over pressure 2 equals temperature 1 over temperature 2. An example of a problem in which we will use Gay-Lussac's law. In this problem, the pressure in a sealed can of gas is 245 kPa when it sits at room temperature of 20 degrees Celsius. I'm sorry, I forgot to write that. And if the can is warmed to 48 degrees Celsius, what will the pressure inside the can be? Here's the equation of Gay-Lussac's law. First pressure over the first temperature equals the second pressure over the second temperature. I have now written down our given, being the first pressure being 245 kPa, the first temperature at 20 degrees Celsius, and second temperature at 48 degrees Celsius. Since this is the given, we are looking for the second pressure. When computing with gases, temperatures must be converted into Kelvin units, into Kelvin temps. Now, with degree Celsius, all you need to do is take the amount of degree Celsius and add 273 to get the Kelvin temp. Here, I have written it down. Now, since we are given the first pressure, the second temperature, and the first temperature and the second, we are looking for the second pressure. And to start off the equation, we need to cancel out the second temperature by multiplying it to both sides. This results in canceling out the second temperature on this side, leaving our equation to be T2 times P1 over T1 equals P2. We will, so that it may be easily understood, I will transfer the second pressure to the left side. So this is the equation that we are working with. To get the second pressure, first we take the second temperature and multiply it by the first pressure. And remember, temperatures must be converted into their Kelvin temps. Now here is our T2, or the second temperature, which is 321 Kelvin, and the first given pressure, which is 245 kPa. Over our first given temperature, which is 293 Kelvin. Now for this, we may use our calculators. After doing so, we are given 268. My calculator gave us a rather long number, but I rounded off the first three numbers, and this is what I got. Now to get the unit, we'll just have to cancel out the 2 Kelvin units, and we are left with kPa. And here we are given our final answer. Avogadro's law states that equal volumes of all gases at the same temperature and pressure have the same number of molecules. The law is named after Amadeo Avogadro, who hypothesized that two given samples of an ideal gas with the same volume, temperature, and pressure would contain the same number of molecules. The formula for this law is written as first volume over first amount of gas in moles equals to the second volume over the second amount of gas also in moles. Here is an example problem in which we will apply Avogadro's law. If 2.4 moles of gas occupies a volume of 60 liters at a certain temperature, what volume will 3.7 moles of gas occupy? Here I have written down our given. The first amount of gas being 2.4 moles, the first volume 60 liters, the second amount of gas 3.7 moles, and we will be looking for the second volume. Here's our formula which we will use in order to get the second volume. V1 over N1 equals V2 over N2. Now I have written down our given V1 being 60 liters, N1 being 2.4, V2, we're looking for that, and N2, 3.7 moles. First we have to cross multiply. 60 times 3.7 and 2.4 times V2. You may use your calculators. With that, we will get 222 equals 2.4 V2. Our next step, we will have to divide both sides by 2.4. Now, we will cancel out on this side since they are equal. And here, if you are to use your calculators, we would get 92.5 equals, since this remains as V2, so V2 equals 92.5. and unit of measurement we'll use are, since we look for volume, it will be liters. And that is our final answer for this problem.
The ideal gas equation. First, what is an ideal gas? An ideal gas is a hypothetical gas that satisfies or follows all assumptions of the kinetic molecular theory. Moreover, the ideal gas molecules have no intermolecular forces of attraction. Thus, their volume is negligible compared with the container's volume. The ideal gas equation is actually a combination of Boyle's law, Charles' law, and Avogadro's law, particularly their relationship. So, the first one is the relationship volume is inversely proportional with pressure. This is actually Boyle's law. The second relationship is volume is directly proportional to temperature. This is the Charles' law. And the third one is volume is directly proportional with the number of moles. This is your Avogadro's law. If we combine all of these relationships, we can have volume is directly proportional with the number of moles and temperature, and volume is inversely proportional with pressure. Now, simplifying the relationship, we can now write volume is equals to NT all over pressure multiplied with a constant K. This particular constant is actually your R, or what we call the gas constant. The gas constant would embody how an ideal equation satisfies all the assumptions of your kinetic molecular theory. We can simply write this further into V is equals to nRT all over P. Now, to make the equation much simpler, I will be multiplying both sides of the equation with pressure so that I will remove the fraction on the right side. PV is equals to nRT. This should be our main equation for the ideal gas equation. I hope you understand how the ideal gas equation was brought about by combining the Boyle's law, Charles' law, and Avogadro's law. R, again, is called the gas constant. Since it is a constant, it has the value 0.0821 liter atmosphere over mole Kelvin. There are times for ideal gas equation problem that the gas that is of focus will be undergoing an STP condition, meaning to say standard temperature and pressure. That means your pressure should be 1 atmosphere. Your temperature, the standard is 0 degrees Celsius or 273 Kelvin. And then for the number of moles, 1 mole of an ideal gas occupies 22.4 liters. How is that the gas constant is 0.0821 and why did it come up to this value? Using our main equation, PV is equals to nRT at STP conditions. So kindly solve for R. Divide both sides by NT. We will be having the equation R is equals to PV all over NT. To solve for R, we are under STP conditions. Pressure should be 1 atmosphere. Volume should be 22.4 liters. And the number of mole will be 1 mole multiplied by the number of temperature, 273 Kelvin. Input this one in the calculator. We shall have the value 0.0821 liter atmosphere over mole Kelvin. So this is how the value for the gas constant came about. Again, this slide will just show you the standard temperature pressure values. Your R is 0.0821 liter atmosphere over mole Kelvin. The STP for pressure is 1 atmosphere, but I want to show you the conversion factors from atmosphere to millimeters mercury, atmosphere to torr, atmosphere to Pascal, atmosphere to kilopascal, and then atmosphere to PSI. Then, temperature, 273 Kelvin, and volume is 22.4 liters. We will be using these values later on. In order to fully understand the concept of the ideal gas equation, we prepared sample problems. Number 1. How many moles of gas occupy 72 liters at a pressure of 1.9 atmosphere and a temperature of 288 Kelvin? Number 2. A 4-liter chamber contains 1.08 moles of hydrogen at 6.8 atmosphere. What is the temperature of the gas? The third one is, what is the pressure of a 2-mole sample of radon if it occupies 6 liters at 373 Kelvin? And the last is, 2.5 moles of helium gas is at a pressure of 1.70 atmosphere and the temperature is 314 Kelvin. What is the volume of the gas? The sample problem number 1. How many moles of gas occupy 72 liters at a pressure of 1.9 atmosphere and a temperature of 288 Kelvin? The given. The volume is 72 liters. The pressure is 1.9 atmosphere. The temperature is 288 Kelvin. And the gas constant is 0.0821 liters atmosphere over mole Kelvin. We are required to find the number of moles. Now, using the ideal gas equation, we need to derive another formula that will come up with an answer in the unit mole. So, divide both sides by RT, cancel, and we will be having the equation N is equals to PV over RT. Next is to substitute the values in the equation. N is equals to PV over RT. The pressure is 1.9 atmosphere times the volume, which is 72 liters, all over R, which is 0.0821 liter atmosphere over mole Kelvin, times the temperature, which is 288 Kelvin. Now, if we put this in the calculator, we will come up with an answer 5.785627. And since the last operation is division, we shall ascribe to least significant figure. So the least significant figure is 2. So I will round up my final answer up to 2 significant figure, and that is 5.8. To find the unit, just cancel, and cancel. And we will be left with the unit moles. And that is how you find the temperature using the ideal gas equation. The sample problem number 2. A 4-liter chamber contains 1.8 moles of hydrogen at 6.8 atmosphere. What is the temperature of the gas? First, we are going to determine the given. The volume is 4 liters. The number of moles is 1.08 moles. The pressure is 6.8 atmosphere. And the gas constant has a value of 0.0821 liter atmosphere over mole Kelvin. And we are required to find the temperature in Kelvin. So using the ideal gas equation, we are going to derive a formula that will lead us in finding the temperature. So, divide both sides by NR, cancel, and we will arrive with the formula T is equals to PV over NR. Next is to substitute the values. T is equals to PV over NR. The pressure is 6.8 atmosphere times the volume, which is 4 liters, over the number of moles, which is 1.08 moles, times the gas constant, which is 0.08, 21 liter atmosphere over mole Kelvin. So cancel, 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 cancel. So we are going to input these values in a calculator. We have 306.7623, and we are going to round it off to the nearest whole number, in which we are going to obtain 307 Kelvin. And that is how you find the temperature using the ideal gas equation.
Problem number 3. 2.5 moles of helium gas are at a pressure of 1.70 atmosphere and the temperature is 314 Kelvin. What is the volume of the gas? So in this problem, we're going to solve for volume. Let's determine the given. The value of pressure is 1.70 atmosphere. Volume is blank because we're going to solve for volume. Temperature is at 314 Kelvin and the number of moles is 2.5 moles. And now we're going to rearrange the equation so that we can solve for the volume. We only have to do is divide both sides by P. So we can cancel it out. Cancel. And now our equation is V is equal to nRT divided by P. Now we can substitute this given into the equation. V is equals to 2.5 mole times 0.0821 liter times atmosphere all over Kelvin times mole times 314 Kelvin. All over 1.70 atm. Now we can cancel out the same units. Cancel, 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 cancel. So the only left is liter, and it is appropriate because we're going to solve for volume. Then now we can multiply this into this 3 and divide it by 1.70. So 2.5 times 0.0821 times 314 divided by 1.70 is equals to 37.91088. And the use of the significant figures, we can round it off and it will be 38 liters. And this is the final answer. Let's move on to the sample problem number 4. What is the pressure of a 2 mole sample of radon if it occupies 6 liter at 373 Kelvin? So the given is pressure is blank because we're going to solve for pressure. Volume is 6 liter. Temperature is 373 Kelvin. And the number of moles is 2. Now,
we're going to rearrange this equation so that we can solve for pressure. All we have to do is divide both sides by V so we can cancel it out. So, the equation is P is equals to nRT divided by V. Now, let's substitute this given into the equation. P is equals to N is 2 mole times 0.0821 liter times ATM divided by Kelvin times mole. And times 373 Kelvin divided by all over 6 liter. Now we can cancel out the similar units. Liter cancel, Kelvin cancel, mole cancel. So the only left is atmosphere, and it is appropriate because we're going to solve for the pressure. So 2 times 0.0821 times 373 divided by 6 is equal to 10.20776. And by the significant figures, the final answer will be 10.2 atmosphere. And this is the final answer.